Calculus is a mathematics of change. In algebra, college algebra and pre-cal, we worked uniform motion problems that were dealt with average rates of change, right? In calculus, we can talk about not just average rates of change, but instantaneous rates of change. Let's talk about a college algebra problem. Here, I show a graph where the independent or the x-axis measures time, and the y-axis or the dependent axis measures the distance that we travel. So if this graph here represents my trip from, let's say, Waco to Dallas, because that's about 100 miles. I start out right here, and I haven't gone very far at the beginning, but as I get on the interstate, my speed picks up. Well, then it levels off because I have 4 children and dogs that like to travel with me, and they have to stop because somebody's got to go potty, somebody's going to be hungry. So we stop right here, and as the time goes by, we've stopped, and we're not making any distance progression. But at the end of 4 hours, I then reach my destination, and so from here to here, I can talk about an average rate of change. And the average rate of change would be equivalent to the slope of this secant line. So the slope of this secant line would represent my average rate of change. Now, how do you find the slope of any line? I know we let m represent the slope of a line. It's the change in y values over the change in the x values. This Greek symbol delta here, which looks like a triangle, just means change. And as you progress through your mathematics courses, we use more and more symbols to replace concepts. And so if I write something like this that you don't understand or it doesn't make sense, just ask for clarification and I'll explain it. A lot of getting mathematics down is learning to interpret the symbols or translate the symbols. So the slope of any tangent line, remember, is y2 minus y1 over x2 minus x1. Now that looks like the slope formula that you're more familiar with. Well, my first point right here is the point 0, 0. When I started out at time equals 0, I've traveled 0 miles. And then up here I have a point for 100. So what was my average speed over that trip? This is the part where you respond. It's 25 miles per hour. It was my average, even though there's interstates there, but because the kids made me stop for so long, because they just had to have McDonald's, we had to, it slowed down my trip. Now, does that mean that from the time I left my house to the time I arrived at my destination, I was going 25 miles an hour? No, it doesn't mean that. Matter of fact, I was probably speeding along the interstate right here with this line of steepest, right? So this is an average rate of change. We use 2 points and generate what's called secant line to get your average rate of change. In calculus, what we're going to be interested in, by the way, this is the average rate of change. If I wanted to know how fast I was going right here at hour 1.25, what I would be looking at would be the line that's tangent to this curve right here. That would be the slope of my tangent line, and the slope of a tangent line is an instantaneous rate of change. Now, I'm not going to tell you how to get that instantaneous rate of change just yet. That's calculus. But I wanted you to see how we've switched from the world of algebra to the world of calculus. We're moving from needing only 2 points to figure out an average rate of change to now we're going to be able to tell the slope of a curve at a point. Okay, so that's where we are hopefully heading. So this definition is in your book. It's the formula for an average rate of change of y. Notice I said it's the change in y over the change in x. There's the delta. I also told you that this was the slope. M we use for a slope. There it is. So this is the slope of the secant line, and it's this formula I gave you right up here. This right here is y2 minus y1 over x2 minus x1. Remember, using the function notation, and I know I'm really reviewing, but I really want you to remember your algebra. Y is equal to f of x. This is just like saying y equals f of x sub 2. Looking at this graph, then, what we see is instead of using the notation here where we have x2 minus x1, which is represented by this distance right here, we just let that change in x be denoted by a single variable h. That's where we get this part of the formula from. This came from this step right here. If we let h be the difference between x2 and x1, we end up with this formula. These are all equivalent. This is the slope of the secant line. You find it by finding the change in y over the change in x, which is the difference between the y values over the difference between the x values, which is the difference between the y values, so we're still looking at the difference here, between y2, which is x1 plus h, that delta or that difference, minus x1. Another way of expressing x2 is x1 plus h. Does that make sense? We're just learning how to interpret the picture here. What I want you to understand is all of these are equivalent, okay? It's just a different way or different notation for the same thing. They're not different formulas. And so once you get the notation down, it's going to make the calculus part a lot easier. So if you have questions as we progress, like where did that come from or what is this, please ask. All right, and I think the pictures will help to make this a little more apparent. We're looking at this right here, this picture, the slope of the secant line, there's the secant line, and we end up with these points from delta y over delta x, which is f of x2, that's this y value right here, minus f of x1 all over x2 minus x1. But instead of writing x2 like this, we could have used this notation to say x2 is equal to x1 plus h, where h is this change right here, the difference from here to here. That whole thing is h. Any questions? Okay. Moving on then. Let's look at some homework problems that are going to use the secant formula, or the slope of the secant line. It says in exercise 1 through 6, find the average rate of change for the function over the given intervals or intervals. Here's the function, g, and here's, in the first problem, the interval goes from 0 to pi. In the second problem, the interval goes from negative pi to pi. So in order to use this formula for an average rate of change, we need an x1 and an x2. We have that. Right here, this would be x1, this would be x2. G of x1 is going to be g of 0. Well, that's 2 plus cosine 0. And what's cosine 0? Cosine 0 is 1. So g of x1 is 3. G of x2 is going to be g of pi, because this right here is x2, where the pi is. And that's going to be 2 plus cosine pi. And what's cosine pi? Negative 1. We're up on our trig, right? I will provide you with the unit circle for your exams, so if you don't have all of your special angles memorized, you can fudge a little if you know how to use the unit circle. All right, 2 minus 1 is 1. So in the instructions here, we were asked to find the average rate of change. Well, the formula for the average rate of change is g of x2 minus g of x1 all over x2 minus x1. But we know numbers that we can plug in for this now, right? So what am I going to plug in place of x2? 1 minus 3 over, what's x2, minus 0. So this ends up being negative 2 over pi, and that's our final answer. That's the average rate of change. The average rate of change, if you remember, is just this formula right here. Change in y over, it's just the slope of the line passing through those 2 points. You need to know the x's and the y's. We were given the x values. We had to find the y values, and we found them, and then we plug them into the slope formula. Now let's do this one. We want to find the average rate of change from negative pi to pi. What is x1? Negative pi. What is x2? Pi. So we now need to find g of x1. That's going to be g of negative pi, which is 2 plus cosine negative pi, and cosine of negative pi is, well, it's 2 minus 1, which is 1. And then we need to find g of pi, which we already have, because it's the same as it was before, and that is 1. So to get the formula for the average rate of change, we look at the change in the y values over the change in the x values. So that's g of x2 minus g of x1 all over x2 minus x1. What is g of x2? What is g of x1? All over pi minus a negative pi. So that's going to be 0 over 2 pi. So the whole thing is 0. What kind of line has a slope of 0?
Horizontal.
Horizontal line. That's going to become very important to us later on. Any questions about the arithmetic or anything with these problems? Do you see how the formula for an average rate of change is just a slope formula? There's nothing magical about it. Yes, sir.
In the book, does it have a review over like what the tangent of pi or like cosine of pi or secant will be?
There's trigonometric formulas at the very, very back of the book that reviews trig. What I'll do is on Blackboard, I'll post to you the formula sheet I'll give you for the exams, so that way you can print it out and have it with you as you do your homework and you get familiar with it. It has the unit circle on there, so you can use that. But I'm expecting that you know that tangent is sine over cosine when you're looking at a unit circle. The x value is cosine, the y value is sine. But trig is a prereq for this course. And life would be easier in a perfect world if you'd have had trig first, but we'll manage, okay? This is kind of a pictorial representation of what I've already told you. And that is, as we take this point and we get this point from, do you see the point P and the point Q here? What we did with each of these secant lines is we slide this point Q closer and closer and closer to P, so that eventually what we end up with is the slope of the tangent line. Do you see that? As P and Q get closer and closer together, as we slide Q closer and closer to P along this curve, these secant lines are actually approaching the tangent line. And when I said calculus is the mathematics of change, we want to know what that instantaneous rate of change is. So how can we turn a secant line into a tangent line? Well, if you look at the slope right here for the average rate of change, if I let h get closer and closer to 0, remember, h is the distance between the x values, right? If I let h get closer and closer to 0, as this distance right here between P and Q gets smaller and smaller and smaller, doesn't the secant line approach the tangent line? It does. As Q gets closer to P, the slope of the secant line is approaching the slope of the tangent line. And the tangent line, the slope of the tangent line, is our instantaneous rate of change. This is our first introduction to a limiting process, or a limiting concept. Here is a situation in which we have the time that's elapsed, that's measured in days, and the number of flies in an experiment, the growth of a fruit fly population in a controlled experiment. And we have the average rate of change over 22 days. That's what this line right here represents, is the average rate of change of flies over the 22 days. Delta T right here represents the distance from here to here, and that's a distance of 22 days. So the secant line right here represents the average rate of change in the flies over the 22 days. So apparently our number of flies is changing at 8.6 flies per day on average. Now, because OneNote layers colors, if I don't erase these yellow marks, you won't be able to see this graph. So I'm erasing them, but this is why it's to your advantage to print out the notes before class, so that you can make highlights and stuff, marks on your notes in class, or go back and watch the videos. In figure 2.6, which is this figure right here, this is out of the book. What we're looking at is a trend, or for the average rate of change. So this is the position and slopes of 4 secant lines through the point P on the fruit fly graph. And this is explained in your notes as well. So what we can see is as Q moves closer and closer to 23, as the point for Q gets closer and closer to the point for P, we're seeing not an average rate of change, but an approach for an instantaneous rate of change. As Q gets closer to P, H is getting closer to 0. Remember, H is the difference between the distance between P and Q's X values. As Q gets closer to P, H is getting closer to 0, and the slope of the secant line is getting closer to the slope of the tangent line. Now, why is this a big deal? Well, because your average rate of change is the slope of the secant line, and that's from our college algebra days with the uniform motion, distance equals rate times time kind of thing. And our instantaneous rate of change is the slope of the tangent line. And we're wanting to see how we approach this instantaneous rate of change. Now, the last problem that we're going to look at in section 2.1 is number 10 from the homework, and the instructions say to use a method in example 3 to find A, the slope of the curve at the given point P, and B, the equation of the tangent line at a point P. Well, what we need to do is we need to see what the value of the secant line is as we get closer and closer to 1. And we can approach 1 from both the left and the right and kind of get an idea of what's going on. Now, I'm going to see if I can pull up our calculator, because this would be easier to do on the calculator. So I'm going to clear out the calculator, and I'm assuming you know how to put the functions into the calculators. You always want your calculator in radian mode, and for this I need function mode. If you hit mode, make sure that everything on the left-hand side of the screen is lit up, and that way your calculator will function properly in calculus. So we're going to clear we're going to quit, hit second and then quit to get out of this. And then we're going to hit y equals. So let me clear this keystroke. So we have y equals. Now the first thing we want to do is we want to type in our function. Our function here was y equals x squared minus 4x. Y equals x squared minus 4x. Okay, and this is the graph. And we want to know what's going on close to 1. So I'm going to set my window for this to go from negative 2 to 1, 2, 3, 4, 5, just to get an idea. And I don't know what the y values are going to be, so I'm going to let the calculator decide. No, I'm not. Let's go from negative 10 to, I think 4 would be sufficient. We'll try 5. And then we're going to look at the graph. And here's a graph of the function. And what we're saying is, right here, we want to know what is the instantaneous rate of change right here at this point where x is equal to 1. We want to know what is the slope of this tangent line, and then we want to write the equation of the tangent line. So what we can do to figure this out is go to your calculator, to the table. And I'm going to show you how to do this on the calculator, second table. And what we see here is we see a variety of values of x. If you want to set the parameters for your table, hit second window. And what I have this set up to do is to ask what our independent and dependent variables are. So let me go back to the table. And we want to let x go. I'm going to clear all these out. We need to clear the table. Let me see. It's been a while. Highlight the x. It's not letting me do it. Alright, well I guess I'm going to have to type over. Because I want to know what's happening close to 1, I'm going to start to the left of 1. And let's let x be 0. If x is 0, then y is 0. Can I get closer to 1 than 0? How about 0.9? That's close to 1, isn't it? How can I get closer to 1 than 0.9? 0.99. How about 0.999? That gets closer. That's a point to the left of 1. How about to the right of 1? 1.09. Can I get even closer? 1.01. That's closer. Can I get closer? 1.001. 1. Now look at what's happening with the y values here. As we get closer and closer to 1, what is happening to the y values? What I need, though, is another column where I can calculate the slope, because I don't really want to know what the y value is doing. I want to know what is the slope doing. So what we need to do is create a table here. So this is giving us several points so that we can look and see what is happening to the slope of the line. So this column here, I need to have the slope of the secant line. But in order to get the slope of the secant line, I need a formula. Is there a way to do that on this, or do I have to use the table? That's fine. So here's what we're going to do. We're going to go into Stat. I want to edit a list, so we're going to hit Edit. And here's a whole bunch of lists, and I'm going to clear them out. Hit Clear, Enter, hit Clear, Enter. And I want to populate this list with what I have in X. So let me see if this will work. I'm going to type in the numbers that are close to 1. We have 0.9, 0.99, 0.999. That's getting close. To the right, we have 0.001, 1.001, 1.001, 1.01, and 1.1. Do you see how I'm getting closer and closer to 1 from the left and from the right here? What I'm doing is I'm letting these x values approach 1 from the left and from the right, coming in on 1. What I'm going to do then is I'm going to have to tell the calculator how to figure out what goes in place of the y. So I'm going to type in a formula. So we highlight list 2. The formula is going to be x squared, so that's going to be list 1 is our x's, secant number 1 squared, minus 4 times secant number 1, that's list 1, or x. And then the calculator, if you hit enter, it will automatically populate list 2 with the y values. Do you see what just happened?
What was the formula for L2?
If you go over to L2 and you highlight this, what I typed in was x squared, which is list 1 squared. You hit secant 1 and then square, and then minus 4 times list 1, because our x values are list 1. And then it will populate this with the y values. List 3, I want to be the slope for these points. So I'm going to highlight list 3, and I'm going to use the slope formula here. How do we find the slope? It's the change in y over the change in x, right? So for this formula, I need open parentheses, because I'm going to have a difference on top of a fraction, the difference on the bottom of a fraction. It's got to be in parentheses. All right, so list 3 is going to be y2. Yeah, y2 we're going to let be the y values that are calculated here. So that's secant 2 minus the y, those are the q's, minus, and then we have our point P, which was at 1, negative 3. The y value there is negative 3, divided by our x values, which is list 1, minus our x value here was 1, and this came from the problem. Do you see the problem right here? Here's the x's and the y's that we calculated. And we wanted, these are for a point Q. That's to the left and to the right of P, so we can see what the slope is going to be.
Y over X.
Yeah, it's changing y over changing x. At this point P, that's why I used the negative 3 and the 1 for the x's and the y's in the formula here. And you got to look at this now, because this is going to go away and you'll have to watch the video to review and see how I punch this into the list. And then you close the parentheses for the denominator. Okay? Hit enter, and what list 3 is now is it's all of the slopes as we go from, and we want to know what is the slope approaching. So let me copy this and put it right here. So list 1 were the x's that were close, approaching from the left. These are as we get closer from the left of the point. And then these x's right here were approaching from the right. We're approaching 1 from the right. So here's the x's, the y's, and then this right here is the slope of the secant line. And as we get closer and closer to 1, what is the slope of the secant line approaching, do you think? It looks like the slope of the secant, or the slope of the tangent line, is going to be -2, because that's what all of these secant lines are getting closer and closer to, is -2. So we would use that then for the slope of the tangent line, just based off of this graph. Do you want me to write above here how we came up with these? Let me write it below. Yeah, I think that would prove helpful. So the x's here was going to be, the x's, I just put the numbers in. And these are the numbers, how I selected the numbers. They were numbers that were getting closer and closer to 1 from the left, and then closer and closer to 1 from the right. And then to get the y's, I said y is equal to, and I did this up in list 2 with L2 highlighted. We have y equals, and then this was L1, which you get by hitting second 1, because if you look right above the 1, it's the L1 there, squared minus 4 times L1. And then for the slope of the secant line, with L3 highlighted, the slope of the secant line is equal to, open parentheses, L2 minus -3 divided by L1 minus 1, and then close the parentheses. Does that help? Changing y over changing x. But this is how you can use your calculator to handle a bunch of complicated number crunching. Last semester, when you look at the video, I didn't do that, and it was more complicated and ugly, and so you really want to watch the video for this one. Yes, sir?
This is kind of like going way back, but how do you, when you're on the table, how do you get the x values to be like 0.999?
Okay, let me go back to the calculator, because that question's come up twice now. If you go to second table, and you do, this is the table, and you want to know how did I put in those numbers, if you go to second table set, which is right above the window, and right here for your independent variable, highlight ask, then it lets you put in the numbers. But if you have auto, then it's going to start populating based on where you tell it to start and what the delta is.
So how do we know what to put in those numbers? Is it always put in?
Okay, how we knew what to put in was numbers to the left and the right of this x value here. Because we wanted to find, these are great questions, by the way. Let me go back to the graph. Our goal here with this problem was to find the slope of the curve at the point P. Here's the point P right here. You see where the blue blob is now? As we approach from the left-hand side, we have this red arrow, and that represents the x's. And from the right-hand side, I have this green arrow. And that's how I determined the left and the right here, and that's where I came up with those numbers. So because we were approaching x equals 1, to the left here, I picked points that were getting closer and closer to 1. 0.9 is close to 1, 0.99 is closer, 0.999 even closer. And then as I approach from the right-hand side, 1.001 is really close, and then I started, I probably should have done this the other way, but I wanted you to see the 2 coming up in the middle, the -2. But you asked, how do we determine what you plug in for x? The answer is, you look and see at what point you're approaching, and you go to the left and the right of that number for the x. Does that help?
And you're always dealing with x?
Yeah, the x is the independent variable. Notice whenever I just punched in the numbers for the x's. I had to put in a formula to calculate the y's and the slope. The formula for the y's is this function here where I have y equals, and it has to be given to you. So this is what you use for your function. And then this is the slope of the secant line, which is changing y over changing x. Here's the x, here's the y, and then here's the other x's and y's. That's why I said use the list for the x's and y's that are changing. Use the -3 and the 1 for the x's and the y's that are not. Does that help explain it?
Yeah, how do you get back to the list of like L1, L2, L3?
You hit stat. If you go to your calculator, there's a button right there that says stat. Hit stat and then edit, and there's all of your lists.
Okay.
And anytime you want to clear a list out, you can't just delete that item. Highlight the list and then hit clear. So this takes care of a lot of number crunching that was tedious and confusing last semester. We're not done with this problem. We still have part B to do here. Part B says write an equation of the tangent line. All I've found right now is the slope of the tangent line. This was part A. Part A says the slope of the tangent line. So this right here is part A. And we got it from observing what was happening with the table, right? Part B is to write an equation of the tangent line. So for part B, I need to write an equation of the tangent line at the point 1, -3. Now you need two things in order to write an equation of any line. You need a point, got it, and you need a slope, got it too, right? The point gives us the x and the y. The slope is -2. So we remember from our algebra days, we can use y equals mx plus b to write an equation of a line. And what do I plug in place of y? -3. What do I plug in place of m? -2. What do I plug in place of x? 1 plus b. That's a b, not a 6. My handwriting sometimes hurts. This is going to be -3 equals -2 plus b. Now what? All right, add 2 to both sides, and we get b is equal to -1. So the equation of the tangent line then is y equals -2x minus 1. This is the equation of the tangent line. We used our point, we used our slope, and y equals mx plus b to find the equation of the tangent line. You will have to know how to do that.